Okay, what's up, guys? Welcome to our today's tech talk. Lou and I worked previously together at a startup that was acquired by Bazaarvoice, which you see on this beautiful slide right here. He's a joy to work with, and what I love about him the most is that he's so successfully and impressively spans the boundary of a scientist and engineer. So I hope that everybody here can, learn something. He ran projects from the ideation and research stage through the deployment at scale, which I think is just so incredible that you can go, from one extreme to the other and be successful at it. And I learned a lot from him, and I hope today that you all will too. So with that, Lou, take it away.
Thanks, Thomas. Yeah, so sorry about the slow start there. It's always a challenge when we're remote. Thanks for having me today. So full disclosure, I hadn't heard of FAIR until Tommy asked me to give this talk. So naturally, I did like what any engineer does. I Googled around about it, saw your guys' really cool blog, The Craft. And it looks like you guys are having a lot of fun. Looks like a great place to work. I have a lot of questions, but none as pressing as hey, where can I buy one of those shirts? And finding a piece of apparel from a photo computationally is an AI problem known as visual search. And that's what I'll be talking a little bit about today. And to motivate this problem, I'm going to share a little bit about what Bazaarvoice does. So our core business at Bazaarvoice is enabling e-commerce brands to display user-generated content on their websites. We started out with reviews, but now we work with all forms of user-generated content, including questions, images, and videos. And to clarify this, I'll show the data flow of a concrete example of one of our products. So we have this product that we call Visual Galleries. And what we do is we gather photos and videos from social media networks, such as Instagram, for our clients to post on their website. The data flow is illustrated here. Our software gathers media from Instagram and lets our clients search, curate, and request rights for the media that we've collected. It also allows clients to associate the media with their products, which in turn results in the media showing on their website's product page. So here's a real example from one of our clients' product pages. And you can see the user-generated photos at the bottom show the products in use by our clients' customers. But for this to work, we need to know what products are in each image that was posted on Instagram. And that's where visual search comes in. And total automation of this with a full AI is extremely hard. A lot of products look really similar, especially blue jeans and stuff like that. So rather than trying to go for total automation, our approach was to recommend products to our clients that we think are in each photo that we find on Instagram, and our clients can confirm it and ship it to their website. So today I'm going to dive deep into the problem and how we approached it at Bazaarvoice. I'll start by discussing our use case and how it's actually a problem of scale. And then I'll review the basics of quantization, which is one approach to solving that problem. And we'll see where the classic approach falls short in practice. Then I'll discuss a recent research paper in the space and how it solves many of the challenges that we face for large billion-scale data sets. And finally, I'll conclude with a peek at how we used it at Bazaarvoice and a few different places it fell into our products. A little bit about myself. I did some graduate studies at Drexel University in Philadelphia, which is it's a small town outside of New York. Maybe you guys have heard of Philly. And there I studied computer vision and machine learning. My research was in video analysis of crowds, which is like a cool little screenshot right there. But I didn't really enjoy academia. So I left from a career perspective, even though I continued to teach. And then I went on to work at a startup called Curelate. That's where Tommy and I worked. And there I did a lot of work transferring research papers into products. So this talk is actually an example of that work I did at Curelate. But then we got purchased by Bazaarvoice, which is why now I say we did all this at Bazaarvoice. But really, we did it at Curelate. And that's where I work now. And right now I'm working on building machine learning operations software to democratize AI across our engineering teams. And even though I've worked a lot in the e-commerce space, I wouldn't consider myself a very good consumer, because my wife kind of finds it hilarious that I only know about brand names because they're our customers, not because I have any idea what they sell or where their stores are. And you might think that computing and apparel, for example, don't have a lot in common, but actually they share a really rich history. So to see this, I think it helps to know how clothes are made. And I only learned this like a few years ago. So if you didn't know that, I don't hold it against you. So this is an animation of a loom. And what it does is it moves the warp threads up and down, and it shuttles a weft thread going in between them. And by changing which warp threads are up and down, you can create different patterns in the fabric. And historically, these patterns are what sold clothing. So, and this was all done by hand. So making patterns required specialized skilled labor. And then in 1804, Joseph Jacquard invented what was known as the Jacquard machine. And this used wooden cards to alternate which warp threads would go up and down. And it eliminated the need for human labor in that case. And after this was invented, textile companies had to deal with intellectual property rights because the competitive advantage shifted from the pattern itself, from who was employed to the pattern itself, which was encoded in the cards. I think you can see where this is going if you know your computing history. The Jacquard loom led directly to the pantograph, which was used to tabulate the 1890 census. This is largely viewed as the first instance of computing at scale. This is a picture of one from the picture is actually from 1919, but the device was pretty similar. And then this was a direct influence behind IBM's punch card computing patents, which led to the transistors and stuff that we have today. You fast forward a few years, and now we have smartphones. And we still have an interesting marriage of computing and apparel in the commerce space. So this is a video from Google's Pixel marketing campaign. It's an example of visual search in Google smartphone tech. It's pretty cool. You take a picture of the shoe and it shows you, hey, that's that shoe and I want to buy it. So let's look at how visual search works at Bazaarvoice. I'm going to show a rough architecture or a data flow and then talk about some of the challenges faced in each piece. Specifically the last piece, which is the piece today's about. So we start out with the data we have from our clients, which are these product images shown on the lower left. And we have a lot of these. They have millions of products. And we have maybe 1 to 10 photos of each product. And what we're going to get at query time is an image from Instagram, which is shown at the top. And what we want to know is which products from their catalog are in that image. So we start out by running an object detector that gives us bounding boxes around each piece of the image and a label as to what kind of clothing it is. So it might detect skirts, sunglasses, things like that. Then we take those sub-images and run them through a convolutional neural network to extract deep learned features. Now I know this sounds really exciting to everyone. And because deep learning is really cool and powering the AI revolution. But what's important here is that the feature that's extracted from the neural network is high dimensionality. So we get a feature X for our query, which is a vector of real numbers, 2048 of them, and a bunch of features YI, one for each image in our catalog data set. And finally, we find the matching images by looking for the catalog feature vector, yi, that is closest to the query vector, x. And this entire talk is about the last step. How do we do that? I'd love to talk more about the deep learning at some point, but I'll have to save that for like a future talk. And this step seems really simple, but it's actually not when it comes to scaling it to millions or billions of feature vectors. So let's dive in. This is where we're going to switch from a marketing talk to an educational talk, technical talk. All right, so let's talk about approximate nearest neighbors. So the problem that we're facing, finding that closest vector from y that's closest to x at query time, is known as the nearest neighbor problem in the academic sense. And the closeness in general terms can be defined by a distance function d. We're going to use the Euclidean distance just to make things simple. And most of the time you see that in literature. Sometimes it's something slightly different, but like a Hamming distance or something. But we're just going to focus on Euclidean distance for this. And the naive algorithm for this is pretty simple. You just go through every feature vector y in our catalog, compute the distance, and find the smallest, right? That takes an asymptotic complexity of linear time, big O of n. The k-nearest neighbors problem is a little bit better for us. In this case, we want to show the user the top 5 to 10 results that are closest to their query vector. So if we do that, the asymptotic complexity increases to big O of n log k. The log comes in if you use a heap, and we'll see an example of that just a little bit. So this is how we wanted to formulate our visual search. The user comes in, picks an Instagram photo, we search their catalog when they open the photo immediately to show them the top 5 or 10 images from the catalog that we think are in the photo. The key thing to notice here is that as y gets large, this can become intractable. And also that distance computation isn't free. Remember, those feature vectors have 2048 floating point numbers. So even though we have like lots of silicon chips, as you scale, this gets really bad. So we turn to approximation to make this scalable. The approximate nearest neighbor problem is a non-exhaustive approximation of the nearest neighbor approach. And the idea is to find feature vectors y that you think are closest to x, but you have some lee room. They might not be the closest, or the distance you compute for them might be slightly incorrect. So the order might be a little bit off. And this is an active area research. It's a really famous problem. And most approaches to the approximate nearest neighbor problem measure themselves by accuracy or speed. And accuracy is computed by a metric called recall at k, which is the percentage of correct feature vectors that are in the top k approximate results. So that means if I were to take my feature vector x, go and find the 5 closest feature vectors in y using a brute force search, then I go and do an approximation and find the 5 closest with that. The percentage of those that are correct is what I'm measuring. So it tells us how often we get it right. And most of the time, if you're comparing approximate nearest neighbor techniques, you're going to find a graph like this that says, hey, I get this accuracy of recall at k, and this is my speed. And you can pick a trade-off between accuracy and speed that suits your needs. But in practice, there's another problem to consider, and that's storage space. So as we get more and more images from our clients, as they sell more and more products, storage space becomes an issue. When you get into millions or billions of feature vectors, it actually becomes a big issue. And you might be thinking, hey man, like hard drives are cheap. S3 is cheap. What's going on here? Well, we can't quite keep it on S3 because we need to be able to search through it. So we said, like, how bad could this get? We started looking at this early on. And if we have a dimensionality of 2048, floating point numbers at 4 bytes per number, then that's 8K per storage vector, per high dimensional vector that we have to store. So that means a gigabyte, we could store about 130,000 of those. And if we wanted 1 million, we need 8 gigabytes of memory. And if we want 1 billion, we need 7.6 terabytes of memory. So it's not so good. And you can compute exactly how much this will cost you if you run it in EC2. So let's say I want to keep all these things in RAM, because that's what I need to do if I want to search it fast. To store 50 million images, it would cost me $3,300 a month, which is pretty bad. Especially we were a startup, so we're like, I don't really want to do that because we already had somewhere around like 5 to 10 billion. So not good. So storage cost is like really part of the equation that we need to look at when we're picking a technique for approximate nearest neighbors. And most approximate nearest neighbor techniques can be broken into one of 4 families. There's trees and forests, which is like the classic KD tree in higher dimensions. It's basically a binary search in more than one dimension. Neighborhood graphs are another technique that comes in, but they still require linear storage space. So we figured that wasn't going to work with us. Locality sensitive hashing was a newer technique that was really taking off about 10 years ago, but has since been replaced with quantization techniques, which is what we're going to talk about today, which is pretty fun. So quantization techniques give us sublinear storage and sublinear query time at the expense of accuracy and other complexities that we'll see. So this was good for us. We didn't want to spend a lot of money storing the feature vectors or spend a lot of time coding a system that would shuttle the feature vectors from S3 onto our local EC2 machine as the web service was running. It really came down to we need to compress that space. Cool, so let's talk about quantization a little bit. Here's a slide to give you a nice throwback to your undergraduate time. And we're going to do a little crash course in quantization and just take the pieces that we need. So a quantizer is a function that takes one of our high dimensional vectors and spits out another high dimensional vector that is from a small set of pre-selected vectors called a codebook. So in this example, Q is our quantizer function. It takes a vector Y and it spits back one of K vectors in our codebook C. And shown on the right here is a little illustration. The blue dots are our codebook C. And in this case, C is only 3 vectors big. So the cardinality of C is typically a lot smaller than our data set, Y. And Y is shown in the red dots. So typically, we want that codebook smaller because then we can just store which index in the codebook we're looking at. We'll see that in just a minute. Most frequently, we're going to train this quantizer on an existing data set. And the common way to do that is an algorithm called k-means. You select your centroids or codebook middles at random. And then you iterate, assigning all the points to one of those codebooks, recomputing the new one as the mean, and repeat. It's an iterative process. So you run it for a while until it converges. And once you have that with your kind of training set, you can use it to do approximate nearest neighbors, or look up which index you're closest to. So let's see an example of that. So once we've trained a quantizer, we want to use it to compress our reference set Y. And then we're going to store that to disk so that it doesn't take 8 gigabytes per millions of images, right? And what we'll do is for every feature vector yi in our big Y here, we'll run it through the quantizer, and we're going to represent it by which centroid it is closest to. So we have one feature vector yi say, hey, quantizer, which feature vector am I closest to? It says, hey, you're closest to the first one. So I'm just going to store that index, which we'll refer to as zi, on disk, which is the number 1. And in this visualization here, I have 3 different vectors in my codebook. So I only need to store the numbers 1, 2, or 3. And from a storage cost, this is great because it means I only need to store log base 2 of k being the size of my codebook, bits per vector. It's bits, not bytes, right? So that's like awesome, right? It's pretty cool. And then once we have that stored on disk, we can use it to do an approximate nearest neighbor lookup. So let's say I have this index on disk that I built on the previous slide. I can also store the cache of the distance of my query vector x to every vector in my codebook. So I get a query vector x in. I say, hey, how far am I from all the feature vectors in my codebook? That's really fast. I can do that because the codebook is much smaller, right? That's the whole idea. And then I go to my index and say, okay, I have all these images in my database, and I want to know which one my query vector x is closest to. So I started the first one, say, okay, the first image is codebook value 1. I look in my cache, I see that distance is 0.4. I throw it in a max heap. Then I do that again for the next image, all the way through the entire data set. And I keep my max heap at the size k, where k is the number of nearest neighbors I want. And what that gets me is a search that's still linear. I still big O of n, but I've eliminated the need to compute the distance, right? The distance is in the cache, so it's big O of n log k asymptotically, but it's super, super fast. We can make it even faster using a technique called inverted lists. And what we do in that case is we store all of the database vectors, their indexes, in an inverted list based on which codebook they were quantized to. So I get my feature vector X in. I then say, oh, okay, X quantizes to codebook 1. I'm just going to go look at those guys and see that come up. So this reduces the complexity to roughly n, the size of my data set, divided by k, which is the size of my codebook, which is pretty cool. One thing to note is like, we're not getting the exact values here. We're getting something close to it with that distance cache, right? So we can measure just how poorly we're doing via what's known as the distortion, which is the distance from each vector in my data set to the quantized value, the difference between the red and the blue dot here. This is known as the distortion. It's just the sum of the absolute value of all the distances. Most of the time we can tolerate this a little bit as long as the number of centroids is long enough. I'm going to ignore this problem for now, but it's going to rear its ugly head later. So let's talk about the wins. The good things here is if we do this, we're going to save a lot of space. So I generated a fake data set with different, and then I ran this quantization for a bunch of different numbers, different size code books. So remember I said like the code book size is what matters. And as you can see, as the number of centroids increase, or the size of the code book, we get a better compression ratio. So compression ratio is the size of the original divided by size of the n. On 1,000,000 images, a codebook size of 1,000 has a compression ratio of 170. That means the resulting size is less than 1% of the original input vectors. So our take home here is the compression's working really well. But the problem is, if we want it to be accurate, we need a large number of centroids. We need that codebook to be really big, right? So if we want our recall at 5 to be, say, 90%, we need almost as many entries in our codebook as we do vectors in our data set, which is not good. In addition, remember I said that k-means algorithm is iterative. Well, the asymptotic cost of that is really high. So it takes like forever to run, like much longer than we want it to. I mean, now granted, you can make the argument that that's going to happen offline when the client uploads their catalog to us, but it's still not great. So take homes like from quantization at the basis is like the compression's good, the accuracy is not so good, and the computational complexity is not so good. So the question is, facing researchers, I think k-means was developed in like the 80s, 1980s, like a long time ago. The question researchers have been spending a lot of their time on over the last few decades is like, hey, how can we save space and computational efficiency? And one technique that was published in 2011 is known as product quantization. You'll see a few other words on top of there because the people kept adding words as we did that. And we're going to get into the other techniques next. And product quantization was a paper that came out in 2011. It's pretty cool. And the idea is really simple. I'm going to take my feature vector y. Remember, I have 2048 floating points and floating point numbers in there. And I'm going to break it up into m subvectors, each of the same size. So like I have 2048 values in there. I'm going to break it up into, I don't know, a bunch, like say 4 or 5 subvectors, or it's usually a power of 2. So let's say like 16 subvectors of size 32 or something. And then I'm going to run k-means and create code books on those subvectors. And I'm going to use some cardinality. They use k prime. I know there's a lot of k's, I apologize. K prime is the cardinality of that I use in those subvectors. So then my quantizer is now a function of a bunch of other functions, meaning I take my vector, I split it up, I run each subvector through each quantizer. And why is this good? Like, what does that get us? On one hand, the quantizer is spitting out more than one number. It's not just one, it's like m numbers, right? What does that mean? Well, what happens is the actual codebook is now the Cartesian product of all the subcode books, which means the number of possible centroids becomes k prime to the power of m. So we're getting an exponential increase there, which is awesome. It also runs a lot faster because the asymptotic cost of k-means depends on the dimensionality, and we've reduced that. So it goes down quite a bit. So what it can do is it'll vastly increase the number of possible centroids. And I realize that's a lot of math. So let's look at an example here. So let's say this is my data set Y. I have a dimensionality of 2. I have 4 vectors in here. First, I split it in half. So M is 2. And then I run k-means on the top and on the bottom. So I run k-means on top with k prime equal to 2 as well, meaning I want 2 centroids in each codebook. So I have 2 codebooks, each gets 2 centroids. The top ones means are -2 and 6, and the bottom ones means are -1 and 7. That means any quantized vector in my original set is going to get turned into a combination of those means, right? So let's label them A, B, C, and D. Well, what are my possible combinations of those subvectors? I could do AD, BC, BD, AC. That's that Cartesian product coming in. Like, how can I combine those different quantized results? So I can get the number of possible centroids increases to k prime to the power of m. In this case, it's 4. Let's see another example where it really like starts to pop. Here I took my my 2-dimensional data set, that example one I showed earlier, and I ran product quantization on it with k prime, meaning the number of centroids in my codebook equal to 3, and m equal to 2. So I just, again, cut these 2-dimensional vectors in half and ran product quantization on it. And that means k prime to the power of m is 3 to the 2, which is 9, right? So I have 9 possible centroids here shown in blue. And I achieved it by running k-means with only codebooks of size 3, right? That's awesome. I just run it twice, getting a logarithmic asymptotic behavior there. But it does look like a regular grid. You'll notice that, that now it's a regular grid because we're slicing and dicing those things together, right? The means get aligned to each axis when you do it. So this is actually pretty awesome. This was like amazing. So first win we got from this is the asymptotic cost is significantly reduced. Here I show the number of operations needed for k-means, which is shown in purple, and then product quantization with different size reference sets for different values of m. And you can see it's like way less, right? Like that's pretty great. Also, we need many fewer centroids, like the number or the value of k prime, meaning the size of the codebook that we're doing k-means with, is much lower. So to get recall at 5 for 90%, remember we saw with k-means that was like really high. We needed almost the size of our codebook. That's shown in dotted line here. If we just cut the vectors in half and do this with m equals 2, we're already doing way better. Like we only need like, looks like maybe 1,000 means to get that. That's amazing with 10,000 reference set. So we've reduced, we've increased the number of possible centroids, but actually reduced how many centroids we have to compute because we do it on half the vector, right? That's awesome. You get that Cartesian product. So product quantization was pretty cool. When it came out, that's when everyone stopped kind of looking at locality sensitive hashing. But there's a few, we could do a little better. How can we do better? So in 2 years later, this paper called Optimized Product Quantization came out. They basically said, hey, I'm looking at this thing, and these blue dots, they probably didn't say this, but I look at it as like, hey, these blue dots are aligned to the axis. It's a regular grid. But the data isn't. It's like kind of aligned off to the right, right? Could we move these things around a little bit to reduce or get better quantization? Or can we move them around to reduce our distortion measure? Remember, that was the difference between the quantization value of our vector and the actual vector, right? So the idea behind optimized product quantization is to transform our vector space to reduce that distortion measure. More specifically, they're going to want to minimize the distortion measure shown here by introducing this matrix R into the equation. So after the quantizer does its thing, you multiply the resulting codebook vector by R, and then you subtract it. Subject to the constraint that we're still doing product quantization, that's the codebooks are in C, and that R transpose R is equal to the identity. So it's a well-behaved matrix. And we're going to assume that the noise, or that Y is normally distributed around a 0 mean. Right? Those are the assumptions made. They came up with a few ways to do this, citing some criterion that subspaces should be mutually independent and you want to balance the variance across different matrices when you're computing R. But all of this was about computing R. So I'll go about how they did that. The algorithm was pretty simple. And those of you who have played around with eigen decomposition, this sounds pretty familiar. The basic idea was do PCA alignment, like mean center the data and rotate it around its primary axis. And then permute the rotations such that the variance in the data gets balanced equally across those permutations. And then just run product quantization on the result. So this is easier to see with an illustration. So here's my input data. And I have shown the primary axes in dotted lines, right? So first, I'm going to rotate all this and mean center it. So I'll move it all over to mean 0, 0, right? And I permute it such that the variance gets distributed along the primary axis. So you'll notice it's not quite stretched out anymore. Then I run product quantization on it, get my regular grid. Cool, I'll used to that. Then I invert R and rotate it back to my regular data space. And you can see, let's compare those results. The blue dots are now more aligned to the distribution of the shape of the data, right? So all we've done is inserted a quick need to compute this matrix R through some eigen decomposition and some nifty shuffling that I know I've not shown the slide on, but I wanted to save some time there. Now we get a lower distortion measure. So we get even higher accuracy. So if we compare optimized product quantization with product quantization, which I just talked about in the previous section, you can see we get a lower distortion on all different values of K. And we also get a higher accuracy on our queries. So this is some synthetic data showing recall at R. Again, 100% is best. And we do well with more neighbors, but the optimized product quantization shown in orange is doing the best. This is from the paper. They did it on a data set of 1 billion size, and they showed that they beat product quantization on it. So this was pretty cool. This was exciting. Throw a few matrix rotations in there. Everything's happening well. But there's a key bit that I mentioned in that slide that can bite you. Specifically, we assumed that the data are normally distributed. And that's not always true. And the next year, these guys said, hey, what if your data is not normally distributed, right? So they released this paper called Locally Optimized Product Quantization to address that. So let's look at an example. Here I have some data that's not normally distributed. In fact, it's multimodal. I have a bunch of little clusters of data. And if I run product quantization on here, the centroids that I get are shown in blue. You can see there's a lot of wasted ones. Like there's a bunch with nobody near them. So I'm just wasting computation space there. So as a result, a lot of the centroids aren't used in between models. The idea behind locally optimized product quantization is pretty simple. First, we're going to run a quantizer on all the data, meaning we're going to run k-means, but with a really small value of k. So we're just going to try to find the centers to all these little globs, right? But we're going to call that a coarse quantizer. And then we'll run optimized product quantization for the data sets that get assigned to each coarse quantizer, which means we get better alignment within each group. So if you compare these two, shown on the left is locally optimized product quantization. I need to do k-means with big K equal to 5, that coarse quantizer first, and optimized product quantization on the right. And you'll see that when you do this, I actually have fewer centroids shown on the left with locally optimized product quantization. I have 4 fewer, I have 45 centroids instead of 49, but I get better distortion. I can get closer to all my feature vectors. And this paper was particularly hilarious to me because if you read the optimized product quantization paper, they actually call this out. And they say, hey, you could use a distinct optimized product quantizer per Voronoi cell, meaning per this coarse quantizer, but it would be memory intractable, so don't bother. And the other guys were like, no, not really. wasn't too bad. It's a little bit more complicated than that, but that was the basic idea. It's like, go ahead and throw it on there. So if you compare locally optimized product quantization to optimized product quantization or product quantization, you can see we get even further accuracy. Our recall at R keeps going up, which is great. And this is a figure from the paper. So that was pretty exciting. So in 2017, a few years after that paper was published, while at Curelate, we did all this looking into this and decided to use it for our visual search problem. So I'll share some of the details about that real quick, because I know we started a little bit late and I don't want to take too much time. So as I mentioned, in 2017, we built it out, which is hard to believe that was 5 years ago now. And we wrote it in C++ using libeigen for SIMD instructions. And then we wrapped a Scala wrapper around it so that we could use it in our microservice architecture. That was pretty fun. So it was like super fast. And what we ended up using for our M was 256 is how much we split it up. And we used 128, codebook size of 128, which meant we could cram 1 billion images into 230 gigs as opposed to 8 terabytes for a compression, for a reduction of 97% in storage, which was pretty awesome. The year after that, we decided to train our own embedding network, which I mentioned we used the DeepNet before, which reduced that 2048 dimensional vector to 128 with the same accuracy. But we still used LOPQ to compress it, which was awesome. And now we could store 1 billion images, feature vectors in 26 gigs. We didn't quite have 1 billion at the time. We had about 10 million, which meant we could store 10 million reference vectors and search it super fast in 256 megs of RAM. The whole thing ran on a Docker container in Elastic Compute Service and cost us like $5 a month or something. Plus whatever I made them pay me to figure it all out, which was pretty fun. We only had an approximation error of 2%. And here's a video of the product actually being used. So the user comes in, they see this user-generated photo. You can see we ran the object detector, and it shows the images from their product catalog that we think are in that photo. So that was pretty cool. And like a good startup, we said, well, what else could we use this for? What other problems could we solve in this space using this visual search? And another problem that often came up was, like I mentioned, we gathered images from Instagram for our clients. That's like millions of images that they see. So they log into our dashboard and would see tons of images. Most of it's not great. And they just want to find the ones they think will look good on their website. And so we said, well, hey, could we use this to surface high quality images, things that look really good? We thought, well, what does quality mean? It's a little subjective. So we asked our clients and they were not helpful. So shown on the left here is a photo that our client approved. They thought it was a high quality. And shown on the right is a photo they rejected and said, that media is poor quality. So we couldn't quite use our client data as what they considered a good image. But we got a few insights into what they liked. So we know that like most clients have a unique visual style that they're going for. You see this in brands like Lilly Pulitzer, where there's like bright pastel colors and things like that. A lot of brands have a really similar color palette they pick from. We also know that like most brands have kind of the same similar kind of content. Like a home goods brand isn't going to be looking for images of, say, pet food or something like that. So that comes into play as well. So our approach to finding high quality images was to build a model for each of our clients using visual search. So we downloaded all their Instagram photos to get examples of their style and content. Then we ran them through a convolutional neural net again to get these high dimensional vectors. And we put them in some high dimensional space. We referred to this as the client style distribution. And whenever a new photo came in from Instagram, we would compute the difference of them to that space. And we would estimate that using approximate nearest neighbors, using that visual search. So we'd say like, hey, give me the 5 closest feature vectors and then take like the average distance and make it exponential or something to make it nice and smooth, right? And once we did that, we found that we could find which images looked like the ones that were on the client's Instagram page. So let's see an example. This is data from Pottery Barn, who I hope are still our clients because I still use the slide. And the shown here are the user-generated photos from Instagram that were shown to them by default. So they're not bad. Like, you know, some of them look pretty good. But if you take the same time in history when we generated this, we went on there and said, give me all the photos from Instagram that, you know, the most recent, they're sorted by most recent, and reorder them by the distance to that distribution, then you can see the images that we recommend to our clients have a real consistent tone and style and content. So that was pretty cool. It was a great example of taking something we built for one thing and leveraging it for something else to do something neat. So I hope I've got you excited a little bit about approximate nearest neighbors. If you want to go and play with approximate nearest neighbors in practice, you don't need to rebuild any of this. There's a project from Facebook called FACE. It's a GPU accelerated implementation of locally optimized product quantization, which is what I just talked about. It's in C++ and Python. It's really good. If that's a little bit too much to get running because you're like using a Mac and it's, you know, whenever you introduce a GPU, it gets a little hard. There's also one from Spotify called Annoy that just does KD trees, does random forests on your disk. Again, we didn't go with that because the storage cost was linear. We needed to compress it. Elasticsearch also, as of like 2019, supports approximate nearest neighbor search. They're using small world graphs, which still have a linear storage cost. But if you're already using Elasticsearch for other stuff, it's a pretty easy way to get started. You just have to be careful that like you know, Elasticsearch storage clusters need to scale with your data. So watch out for that. But that didn't exist when we built all this. And a more recent one's called Bolt. I just heard about this like last week. It's a quantizer that's better than optimized quantization, and it runs much faster. And I haven't played with it yet, but I was reading about it. It looks really cool. So it seemed pretty exciting. Their paper, the whole claim is that they're faster and better than optimized product quantization. Cool. So I hope I've inspired you to dig into research papers when you're facing a technical challenge, and you know, got into the weeds about some of the stuff we use at Bazaarvoice or that Tommy and I worked on at Curelate. And I'm open to questions since I think we have like 9 minutes left.